So next, we prove that z to the power of minus n is equal to the modulus of z to the power of minus n times the ordered pair cosine of minus n times theta sine of minus n times theta. We prove that this statement is true for every positive integer n. So once again, our proof will be by induction. So first, notice that z to the power of minus 1 is the inverse of z, or the reciprocal. This is the modulus, the conjugate of z divided by the square of the modulus of z. So if we restate the complex number z in trigonometric form, we have the modulus of z times the ordered pair cosine theta sine theta, and we are still dealing with the conjugate, and we divide this by the square of the modulus of z. The conjugate of a product is the product of the conjugate, so we have the conjugate of the modulus, and the conjugate of the ordered pair cosine theta sine theta, all of which is divided by the square of the modulus. The conjugate of a real number is the real number, so we simply have the modulus of z. The conjugate of the ordered pair cosine theta sine theta is the ordered pair cosine theta minus sine theta. This is all divided by the square of the modulus of z. Now, as cosine is an even function, cosine theta is the same as cosine of negative theta. And as sine is an odd function, negative sine theta is the same as sine of negative theta. So we have the modulus of z times the ordered pair cosine of minus theta sine of minus theta, all of which is divided by the square of the modulus of z, square of the modulus of z. And so we have the ordered pair cosine of minus theta sine of minus theta divided by the modulus of z. So if we rewrite this, we now have the modulus of z to the power of minus 1 times the ordered pair cosine of minus theta sine of minus theta. Hence the case n equals 1 is true. So we now assume the case k minus 1, that is, we assume that the statement z to the power of minus k, minus the quantity k minus 1, which is z to the power of minus k plus 1, is equal to the modulus of z to the power of minus k plus 1 times the ordered pair cosine of minus k plus 1 times theta sine of minus k plus 1 times theta. We assume that this is true. Then z to the power of minus k is z to the power of minus 1 times z to the power of minus k plus 1, which is the modulus of z to the power of minus 1 times the ordered pair cosine of minus theta sine of minus theta times the modulus of z to the power of minus k plus 1 times the ordered pair cosine of minus k plus 1 times theta sine of minus k plus 1 times theta. Which when we perform the multiplication, we have the modulus of z to the power of minus 1 plus minus k plus 1, which gives us the modulus of z to the power of minus k, times the ordered pair, the cosine of minus theta plus minus k plus 1 times theta, which gives us minus k times theta. And similarly, we have sine of minus k times theta. Hence, the case k minus 1 implies the case k. So by induction, we have that z to the power of minus n is equal to the modulus of z to the power of minus n times the ordered pair cosine of minus n theta sine of minus n theta. The statement is true for every positive integer n. So we have now covered all cases, the negative integers, the positive integers, and 0. And so we have demonstrated that the statement z to the power of n is equal to the modulus of z to the power of n times the ordered pair cosine of n times theta sine of n times theta. And this statement is true for every integer n. Alright? Alright, so new definition. The principal argument of the complex number z denoted arg z, notice the capital letter A, is the unique value of theta, which is an argument of the complex number z, such that theta is in the range from negative pi to pi inclusive of pi. So notice that the set of all arguments of z is the set consisting of the principal argument of z plus all integer multiples of 2 pi. Okay, new definition. The complex number u is an nth root of the complex number z if z is u to the power of n. Alright, so now we come to a new theorem. For all positive integer values n, the complex number z, which we'll put in trig form. The complex number has exactly n distinct nth roots given by c sub k is the nth root of the modulus of z times the ordered pair cosine theta plus 2 pi k divided by n sine of theta plus 2 pi k divided by n, where theta is the principal argument of the complex number z, and k is an integer ranging from 0 to n minus 1. So notice the statement of this theorem is very much like an existence and uniqueness theorem. There are two things that we need to demonstrate. First, that the number c sub k is an nth root of the complex number z. And second, that there are exactly n distinct values for the formula given by c sub k. All right, so now we'll prove this theorem. So the formula c sub k, once again, is the nth root of the modulus of z times the ordered pair cosine theta plus 2 pi k divided by n sine of theta plus 2 pi k divided by n. So if we now raise c sub k to the nth power using de Moivre's theorem, we have the modulus of z times the ordered pair cosine theta plus 2 pi k sine of theta plus 2 pi k. Now since theta plus 2 pi k is an argument of the complex number z, no matter what the value of k, we have that z is the nth, or rather c sub k to the nth power, and hence c sub k is an nth root of the complex number z. Alright, so now we need to demonstrate that there are exactly n distinct values for c sub k. So let the argument alpha be theta plus 2 pi k over n. Now for all values of k greater than or equal to the integer n, alpha can be written in the form theta plus 2 pi j over n plus 2 pi times an integer m, where the integer j is less than the integer n, strictly less than the integer n, and the integer m is n minus j. So in other words, for all values of k greater than or equal to n, the argument can be written in a form such that it is a sum with a multiple of 2 pi. And since sine and cosine are periodic with period 2 pi, there are exactly n distinct values of cosine alpha and sine alpha corresponding to the values of k being in the set of integers modulo n, which again is the set from 0 to n minus 1. And there are n distinct such values. So that completes the proof. So notice that since all nth roots of the complex number z have the same modulus, namely the nth root of the modulus of z, they all lie on a circle in the complex plane centered at the origin with radius the nth root of the modulus of z. All right, new definition. The n distinct nth roots of the number 1, which is the ordered pair 1, 0 in the complex plane, are called the nth roots of unity the set of the n distinct nth roots of unity is denoted U sub n. Alright, so next we'll look at some examples of nth roots of unity. And we'll start with the most familiar, the case n equals 2.